Krishnamurthy. I am associate professor here. I work on networks and distributed systems. I'm also Ray's advisor, who is also going to be taking this class, and taking the class at the same time. So if the class fails, you know whom to blame. Okay, so let me somewhere back to the end of the thing. So let me just I just have a few slides. I just want to kind of talk a little bit about what the class is about. So this is a Quals course that essentially covers foundational aspects in systems. And you should think of this as essentially a gateway course into various systems topics if you're interested in systems research. Or if you're not interested in systems research, this could be the only class that you would ever have to take from the systems area. So we'll be covering topics from operating systems, networks, distributed systems, databases. So it's a mishmash of a bunch of different topics. It's just so that you can sort of bridge your sort of undergraduate knowledge to sort of doing more kind of systems research if you're interested in that kind of topics, or if you want to actually use systems in your own research in whatever topics that you might be interested in. So there's absolutely no prerequisite. So if you're hoping that we would have a class which, where as long as you're enthusiastic for the material, you would just be able to come and take the class. You don't have to have had any prior experience in systems. If you can program a bit, that would be great. If you can't, that's also fine. So it's a gateway course to CSE551, which is an operating systems class, or 552, which is a distributed systems class, or 561, which is a networking class. And these are not offered this year. Is that right? Yeah. So these are not offered this year. So these, but they're going to be offered in the next year, for instance. So you can think of this as a preparatory class for these other courses. So let me just briefly tell you what the major components of the class is going to be and how it's going to play out. So we're going to have essentially a bunch of papers, about 25 papers, which we'll read. These are classic papers. Some of them are more recent papers in systems. We'll pose a question on each one of these papers which you should answer in a blog post before you come to the class. That's going to be one component of the course, and that's going to be a substantial component of the course. That is, you're going to be reading a bunch of papers, fundamentally. There's no textbook, there's nothing else. We're going to have potentially 3 problem sets, which will require sort of doing some kind of coding, some kind of measurements. You can do it in groups of 2, so you can actually have, work with other people, kind of bond with other people as part of the experience. And then do a project which is a research project which explores a research area which is of interest to you. And that's completely up to you. You can do it as groups of 2, groups of 3 if you think it's a very substantial project, or a single person project if you've come up with a really wacky idea which no one else is really interested in. That's totally fine as well. And the best thing is there's no midterm or a final. So there's nothing, you don't have to take any exams at all in this class. And then let me just briefly tell you about the topics that we're going to cover. So we're going to start with really classic papers and systems. Things like, why is the Unix operating system designed the way it is? What are the concurrency issues when you have to sort of program a parallel system or a parallel operating system? Did you know, for instance, Mars mission was almost cancelled because of a concurrency bug? So we actually sent up this Pathfinder mission. It was landing on Mars, and after a couple of days, we couldn't get any sensory data out of it. And the reason for it was a concurrency bug, which is a priority inversion bug, which ended up actually they ended up fixing it from remotely, which is just an amazing debugging experience. And I hope that you go through such amazing debugging experiences as part of this class as well. So that's something which I would like you to do. We'll also talk about congestion control as to how you can bring down the internet if you're not very careful. How to hack, for instance, routing BGP systems and so on and so forth. And then the second half of the course, or maybe somewhat interspersed, are much more recent topics. And I can kind of think of them as falling into 3 categories. One is sort of planetary scale distributed systems. And what I mean by that is, think of Google or Facebook or any of these large scale systems which have like, let's say 20 or 30 data centers distributed across the world, which are basically providing services. How do these things actually work? What are the fundamental building blocks for having such a large-scale system, and how to make that work? So that's one topic which is very close to my research area and something which I'm personally interested in. And it's also going to be a topic which is related to one of your assignments, which is building what is known as the Paxos consensus protocol. How many of you are familiar with Paxos? Okay. A few of you are familiar with Paxos, and those people might run away from the class after hearing this because it's the most hair-splitting algorithm that you can ever imagine. And that's going to be one of the assignments. Don't worry, we will give you a lot of help in terms of how to think about it. There's this really nice paper by Leslie Lamport, which is just 8 pages long. And it looks so simple when you read it. And you feel like, this is the simplest algorithm that one can imagine implementing. And then you delve into the details of what it is. And you realize that lots and lots of interesting issues with it. So the goal is not for you to actually come up with a completely perfect Paxos implementation, because I don't think one such thing exists. Even though a lot of people have taken a crack at it. It's just the process of actually trying to understand how the algorithm plays out in practice. What are the distributed systems components associated with it? How do you reason about the correctness of the algorithm? And I've implemented Paxos as well, so I'll be, a cheerleader, if not anything else, and also help you understand how the system plays out. So that's one component of recent topics. The other one is data center computing. So there's an aspect of how do you coordinate all of these large-scale distributed systems, and then what happens within a data center. And data centers have become really complex beasts. So for instance, if you issue a Facebook request, that is, you go to your Facebook page, what's happening is that you're loading images, posts from hundreds of your friends. If you're me, then I'm not getting any feeds. So, but I'm hoping that a bunch of you are much more social than I am. But what's happening is that a single Facebook page is put together by maybe touching hundreds of different components in the data center, like lots of storage units, lots of compute units, lots of networking units. And you can just imagine the complexity of doing that find, and what is the cost of doing it? What are the bottlenecks in doing that? That's an interesting aspect that I would like to sort of get into. What are the programming models for data centers? What are the performance issues for data centers? So that's the second topic. And then the third topic is mobile computing. So the only thing which matters now is really Google, Facebook, your phone, and distributed services and data centers. That's all that matters. There are only two innovations taking place in systems. One is from the data center perspective, and the other is from the mobile perspective. Everything is going to be mobile in a short period of time. So we're going to look at potentially doing one of the assignments on using Android devices. That's not quite figured out. It depends on whether Google is generous enough to donate a bunch of resources for us. And just kind of understand, do some simple benchmarks, potentially even do a research project in this space, and that's going to be the third kind of special topic that we'll end up covering. And that's pretty much all I have to say now. We're happy to take any questions regarding the class, or what we're going to cover, how the mechanics of the class is going to be. Any questions? Yep.
Can you give an example of what would be an acceptable project?
It's something. It could be as simple as taking. Here's an example. Very simple. Let's say if you would decide to work with Android devices, just take an Android device, write micro benchmarks, understand what the file system looks like, what the process behavior is, maybe context switching time and things like that. It could be as simple as that. So just kind of taking something which is very something which you would like to understand something more about, for instance. It could be, it's fine also to do a project which is more related to the research area that you might eventually end up being in. So for instance, if you're a programming languages person, one thing you can imagine doing is take some of the programming models for data centers and kind of understand how you could potentially extend it in a different way than what's been done before. An example of this is, a bunch of people might have used MapReduce, and it works within a data center. What are the issues in sort of taking MapReduce and working across multiple data centers? How do you reflect the fact that there's sort of essentially multiple levels of memory hierarchy now? How do you make that much more efficient? So that's an example. So we'll have a bunch of sample suggestions that you can think about, but really the best value you would get out of the course is actually you choosing or kind of brainstorming about some new project which would be of interest to you. Okay, perfect. Thanks so much.